Again, dummy variables, regression models. Binary variables. Binary variables are things that can fit into a 0 or 1. Binary. 0 or 1. Two different cases. Either they do or they don't. Male, female. In terms of some particular medical studies, patient is dead, patient is not dead. You can use those. Married or single. Minority or white. These are things you can fit into a binary variable. We'll look at dummy variables for binary variables in a model, and I'll show you how to do more than two options. White, black, Hispanic, etc. Freshman, sophomore, junior, senior. We'll look at how those shift the intercept and slope. We'll look at binary response variables, where you're predicting if something does or doesn't happen. Patient lives, patient dies. Patient or person gets credit score, or person with credit score gets loan or doesn't get loan. We can predict these things, and we'll learn how to interpret those. So here's our example. I like this one in the book. Is there evidence of wage discrimination? Seton Hall professors recently learned the university paid higher salaries to younger instructors and male professors. So men are getting paid more and younger professors are getting paid more. Why would younger people get paid more in the workforce? In some cases, if competition for those people has gone up dramatically, younger people might get higher salaries. Right now, competition for certain jobs is heating up. As the unemployment rate drops to around 5%, and I think we're getting close to a full level of employment, where most people who have jobs want them, and all we're dealing with is frictional unemployment, not as much structural unemployment or cyclical. I think we're reaching a point where it's going to be an employees market, and we can start demanding a little more money as employees. We can say, I might have more than one offer out there. So I think we're getting to that point in the economy right now. Mary Schweitzer works in human resources at another college and has been asked to test to see if there's gender discrimination at their university. So she gathers data on 42 professors, including the salary, which is in years, or in dollars. So that's numerical. We know how to do a test on that. That's our ordinary regression. Salary is our dependent variable. Our independent variables would be experience in number of years. Again, that's a number. We know how to test for that, right? So we can do that. Gender. Uh-oh. That's male, female. So we don't necessarily know how to put a number on that yet. And the age. Well, age is a number, so we know how to do a regression on that. But what if we wanted to test for professors who were, say, above or below a certain threshold? What if we wanted to divide us into so-called younger professors under 40 and older professors over 60? We could assign a dummy variable to that. Using this data set, she hopes to test whether salary differs by a fixed amount between male and female, whether there's a benefit to simply being male, or if there's a difference in age over or under a certain threshold. And we do that using dummy variables. In previous chapters, all the variables used in regressions have been quantitative. They've been numbers, numeric. Now we'll deal with qualitative. Either they are or they aren't. Qualitative dummy variables. A dummy variable for a qualitative value with two categories, there's two ways it can go, assigns a 1 for one of the categories and a 0 for the other. So we're numerically going to change our data. If it's gender, for instance, and we go down through these different professors, we pick a 0 or 1 for whichever one we want to test. Does it matter which way we do it? Not necessarily. Not really. It's really how you want to interpret it. In this case, I will assign 0 to male and 1 to female. So now I would create a variable that might call gender dummy, which would look like this. Right? Now they're numeric, now we can do something with them. So here's our typical regression model, and when we estimate our regression model, y hat, our estimated salary, equals an intercept plus a coefficient times a variable plus a coefficient times a dummy variable, our D here. So we're going to generate a coefficient for gender. We'll run this through Gretel or Excel, and we will generate a coefficient on our dummy variable. And in the cases where our dummy variable is 0, we multiply the coefficient times the variable, right? 0 times anything is what? 0. So in the cases where this is 0, that will drop out. It will disappear. So in this case, if I get we'll say that salary is in thousands. So if I get y hat equals 50 plus let's say I come up with this model. Y hat equals 50 intercept plus 4 times experience plus 6 times dummy. My coefficient, my intercept is 50, my coefficient on experience is 4, and my coefficient on my dummy variable is 6. How do I interpret this coefficient in this case? What have I learned about salary?
If it's a male, you get an extra $6 grand. Or female.
If it's a female, this number is 1, and 1 times 6 is 6, so we would add 6 grand. If it's a male, this number is 0. 0 times 6 is 0, and it wouldn't apply. So there's only 2 ways our dummy variable can turn out, right? Either 6 or nothing. So the proper interpretation is, when this is a 1, it adds 6,000 to salary. So the interpretation of this model would say that our women professors, other things being held constant, are paid $6,000 more on average. What if our coefficient was -6? Then here, when this is a 1, we would say women get 6,000 less, or men get 6,000 more. So that would tell us that this 1 or 0, when it's a 1, I've always thought of it as it sort of switches that variable on. When it's a 0, it does nothing. When it's a 1, it sort of switches that variable on, and now we take off the 6th we add or subtract that coefficient. Questions on how we would do this? Does anybody not see that interpretation? I can go over it again in different ways.
You just made up the 54 and 7.
Yeah, I made it all up. Yeah, I do that often. I have my official statistician's card that allows me to make up numbers. Regression in a dummy variable. The dummy variable shifts the intercept term. It doesn't change your coefficients. It doesn't change the slope of your regression. it shifts, man, it's been a lot, I gotta be careful. It shifts your curve up and down. It doesn't change the slope of your regression line. So this would be your line without a dummy variable. And then adding your dummy variable in will simply shift your regression line up and down. If the coefficient on your dummy variable is positive, it will shift your line up. And if that coefficient is negative, it will shift that line down. It doesn't change the slope, it changes the intercept of your regression line, comparing your predicted y-hat to your x's. So here's our salary, gender, and age. This is the introductory case. So don't necessarily leave aside my made-up numbers. So Y is what? Their salary in thousands. 67,000, 53,000, 73,000. X is their number of years. Can't you see? Could you see a problem with using number of years and age? Can you see a problem using number of years and age? They can be highly correlated, right? Because most of us get out of grad school roughly in our mid to late 20s. You would start teaching sometime after that. So a person who's 50, age would be correlated to the years of experience. But let's say you still thought that the age was really important. You can turn it into a dummy variable and still include information about that age without having two highly correlated variables, and still get the use out of that variable. You can transform it. You can change it into a dummy variable. Y, salary, is dependent on years of experience, a gender dummy, and another dummy for whether or not the professor is 60 or over. So 1 if they're over 60, or what we call an older professor, or 0 if we're under 60, or what we're calling a younger professor. And we can use our ordinary least squares. We can use the same test we've been using. We can run it in Excel, we can run it in Gretel. Nothing special needs to be done. And we'll get a usual coefficient, standard error, t-stats, and p-values. So we have our estimated equation like we've always been doing. Y hat equals 40.61 here, plus 1.13. So how do we interpret this? Every year of experience gets you additional $1,000 in salary. What is the dummy variable 1? That was gender, right? 1 if the professor is male, 0 if female. So what's this model telling us? Being male earns you about $13.92 thousand a year. So we might be starting to find systematic evidence of some type of wage discrimination. D2, older professors. So it's a 1 if they're over 60. So this is telling us that being over 60 earns you about $4.4 thousand a year. So it looks like older professors are being paid more. The difference in salary male-female is captured on the coefficient D1. Why would the age coefficient be statistically insignificant?
It's because of the p-value.
Yeah, we can tell by this high p-value. If the p is low, the null must go. The null assumption is that our coefficient might be 0. The null assumption is that this coefficient is not good. We only assume that the coefficient is valid and useful if we show a very low p-value. What is low? At least under 0.1. Better if it's under 0.05. Really good if it's 0.01 or less. Testing the significance of dummy variables. I'll give you the short answer. We do it the same way we did the other variables. Look at the p-value. We can do the partial F test if we want to do two variables. Look at the p-values. Avoiding the dummy variable traps. You see a lot of people, I'm going to paraphrase what's up here. You see a lot of people try to use dummy variables incorrectly. Someone will try to do this on a test, where you might have several different categories of people. So we might want to test income, how much people make based on their major in college. Okay, so we need a dummy variable because we can't do, we can't say business or technology or liberal arts. So we need a dummy variable here. Okay, so we'll create a dummy variable called dummy major, and we'll make it 1 if this is business, and a 2 if it's a science, technology, engineering, or math field, and a 3 if it's liberal arts field. Outstanding. We've created our dummy variable. Yeah?
I thought you could only use 0 or 1.
Oh, you can! That's the problem with this. Don't do it. Don't do it. No. No. Bad. Alright? What this mathematically says is the STEM value is twice what a business degree is, because 2 is greater than 1, and the liberal arts major is worth 3 times as much, because the 3 is 3 times 1. That's why these numbers don't work. You cannot do this. Someone tries every year, don't do it. Instead, here's how we would do this. We would create a variable called dummy business. And we would create a variable called dummy STEM. Then we would stop. You don't need all 3. The third one is assumed, because these can take on 0 or 1 ranges, right? So we have our different people that we're testing for with different salaries, and if this is a 1 here, can they major in both? They have to be in one of the 2 categories, right? So by definition, if this is a 1, this has to be a 0. And if this is a 1 for this person, this has to be a 0. What if they're both zeros? What do we assume about this person's major? I'm sorry I didn't get my people arms.
Liberal arts.
Yeah, this person is by definition our 3rd category, our liberal arts. So the way we do this is we do 1 fewer dummy variable than the number of categories we have. If we have multiple categories, write that down and circle it. We include 1 less dummy variable than the number of categories. If we created as many as we had, we would create perfect multicollinearity, and our model would be useless. We would create perfect multicollinearity. So we create 1 less dummy variable than the number of categories. Now, in this case, we have to be very careful about our interpretation. We have to think very carefully about our coefficients. How would we interpret our coefficient on dummy business? It's how much more a business major would make. How would we interpret our coefficient on STEM? It's how much more a STEM major would make. And no coefficient, if both of them are 0, effectively neither of those are turned on. And without either of them is how much our liberal arts major would make. We have to be very careful about our interpretation in this case. Questions about how we do this? We'll do examples on Wednesday, and I'll show you some of them. But we do one fewer dummy variables than the possible categories. Freshman, sophomore, junior, senior. You might want to drop freshman and just do sophomore, junior, senior dummy variables, because you have to fit into one of the categories, right? A 1 for freshman negates you from being a sophomore, junior, or a senior. Questions about this and its interpretation? All right. Sometimes we want to do an interaction with a dummy variable. An interaction with a dummy variable. For instance, think back to our, don't read yet, stay on me. I should have talked before I changed it. What if, think back to our professor salary equation that comes with the slides. What if men are rewarded more for their years of education or their years of experience? What if our theory is men are rewarded, or male professors are rewarded more for their years of experience? So we would have to interact two of our variables, whether or not they're male and years of experience. We interact those two variables. The way we interact those is we create an interaction variable that multiplies the x and the dummy variable. So we would multiply here's our years of experience. We would create a years times our dummy variable. In this case, it's 0. What's 2 times 0? 0. 6, 10, 0, 0, 2, again, notice how this is only sort of turned on, activated when this is a 1. I multiply this times this. I interact those two variables. This will help me to determine the interaction of years and the dummy variable. Are men rewarded more for their years than women? In this case, it would be swapped because we got them swapped over here. Because female is 1. So if this was positive, we would say women are rewarded more for staying in a longer tenure than men. The product, the multiplication, this variable, captures the interaction between a quantitative variable, a numeric, and a qualitative variable, a dummy variable. Together, that multiplication changes both the intercept and the slope. So if we interact them, it changes both the intercept and the slope of these variables. There's fewer times when you want to do this, but again, when you want to capture an interaction like this, this is the only tool that will do it. If you think maybe years of experience are more valuable for one group than another, this is the only way to test for that. and hold your other variables constant. So you create an interaction variable. You multiply the variable that you're interested in testing against your dummy variable. Did you have the example with the cars?
I had one.
That I was thinking that there might be an interaction variable there. If you looked at horsepower, does horsepower matter more if a car is supercharged? Horsepower I think would tend to matter more. Having a supercharger lets you get more out of every horsepower. So there might be an opportunity for an interactive variable. If you want to test which car is better, more expensive, etc., having the supercharger makes each horsepower more valuable to you. So you can interact those at dummy variable 0, 1, whether or not it has a whether or not it has a charger, and the numerical horsepower. These are the things I think about when I'm driving in traffic. Testing for significance. Again, our p-values still work. Our partial f-test for joint significance. We're still able to perform standard tests on your interaction variables. We still want to run the same diagnostics. We still want to look at which variables are and are not significant. We still want to look at our R-squared. Man, I'm losing you guys tonight. You all right? We don't want to do hand exercise again, do we? Man, you guys are dropping off fast. What am I doing? Can you put the spider chart back up here? No? All right. I'm done losing. It's not even 8:30. You guys are dropping off quick.
Can we get an example of it?
Other than like the 8 that I've shown? Yeah.
I mean, an applied example.
Yeah. Let me get through some of these and then I'll sit down and do some examples. And I'm going to do them all Wednesday. But let me get through the theory and then I'll show you some of it. Again, we go back to the explanatory case. And we might look at whether gender impacts salary different at different levels of experience. Is experience more valuable for men or women? Do we reward experience for men more highly? So we might look at 3 different models. We consider 3 models. One just has a dummy variable for gender. One has an interaction variable between gender and experience, and one has both. So we might want to compare those 3 models. We've done like 3 homeworks where we've compared this model to this model to this model, and here we'll do it again. 1, the experience, the gender model, and the interaction. And we compare them based on R-squared. And we find that our model 2 has a highest adjusted R-squared, and both of our values are individually significant. Individually significant, it means that their p-values are relatively low. See the p-value in parentheses down here? This is sort of a regression standard to put the coefficient and then the p-value below. So how would we interpret this, remembering that 1 is female and 0 is male? If this is the model we choose to use, we have a positive 0.85. So every year of experience earns you 0.85 thousand or $850 in pay. And our interaction variable tells us that for an additional year of experience, male professors earn an additional... Oh, they got that wrong, didn't they? They got that totally wrong. What is 1 in this, male or female? You sure? I think 1 is male, isn't it, in their example? So this is wrong. Scratch that out. This should say male. This model number 2, is telling us that if 1 is male, men make $850 a year. And for every additional year of experience, they earn an additional $770 on top of that. This would show dramatic evidence of wage discrimination at our university. Not great news. Because the interaction term is in there, it would change both our slope. Yep, one is males here. It would change both our slope here. This would tell us that salary for every year of experience, see how it's increasing at a faster rate for male staff than female staff? This would indicate a problem for the legal department. Questions on that? Let me stop there and run a couple. Let me stop there and run a couple. And there they are. You're welcome. Chapter 17 data files. I think mortgage applications works. Yeah. I'm going to change this. I don't know what the actual variables mean, but I just changed mine. Oh, I can't use this. Damn it. Sorry. It's a different one. Can't use that one. That's a Logit model. It's a different model. We'll get to that one. Oh, come on. Give me something good. Nope. I like it. Longevity it is. So I'm modeling on longevity. Man, I don't like their life numbers. Why does everybody die at like 21? These are weird. I don't like it. Yeah, this is freaking weird. We got. I don't know what these variables are. I'm sure it's something other than longevity. I'm sure it's something other than this.
It's like marriage after 21, so surgery.
I wonder if it's life insurance or something. I don't know what this could be. You know what I'm gonna do? If you got this open, get ready to follow along with me, because I'm gonna get a little nutty here. I'm gonna insert a column between life and income, and I'm gonna call this lifetime, and I'm gonna multiply life by 3. And a half. 4. Four. Sorry, I suck. And we're not going to use this one at all. Ta-da! So, what we're trying to predict is lifespan. I'll change that. So we might be an actuary, and we're trying to predict lifespan. Maybe the higher income you have. I don't know, the more health care you can afford, the better doctors you can afford, the better nutrition, the more medication. So our variable here is 0 and 1. Here's our dummy variable. 0 for male, 1 for female. Drinks. Is this a dummy variable? So this is maybe how many drinks they have a week. So we want to test maybe if they're heavy drinkers, that might affect their lifespan, positively or negatively. Sure, you can quit drinking and you might live longer. Miserable years. So this is what we might be testing. We might also want to test, does drinking affect women more than men? We might does drinking affect women more than men? So in that case, we would create an interaction variable. If we want to know if drinking affects women more than men. So I might create a variable that I call drink interact. And I would multiply number of drinks a week times this dummy variable, like so. And notice how this is only sort of turned on when women is a 1, otherwise this is a 0. It only matters in that case. So I might create this, and now I'm ready to model. I'll just do my modeling in Excel to save time. Data, data analysis, regression. I'm predicting lifespan based on, we'll leave the interaction out right now. Do my first model, which is these three. Stupid number of variables.
What was your X and your Y range again?
My X is what I'm predicting is this lifespan. And my Y, I just did income, women, and drinks, C through E.
Should it be the other way around?
I was gonna say, I think you got it backwards.
Shouldn't want to lifespan?
Well, I mean, I'm sorry, that's what I did, didn't I? Did I do it wrong?
I think
Yeah, you did it right.
said wrong.
I think I did it right but said it wrong, yeah. That sounds like something I would do all day. Okay. Interpret with me. Who jumped right to looking at the adjusted R squared? Come on, be honest. Who jumped right to looking at the adjusted R squared? Don't do it. Don't do it. Signs on your variables first. The sign on income is positive but very small. So this says income might have a positive but small effect. The sign on women is quite large. This says that women live, what, on average 12.8 years longer? That's a lot. And drinks, the sign is negative. So it says the more drinks you have per week, the shorter your lifespan. Okay, liver disease, car wrecks, what have you. Here's our p-values. Turns out that income is not significant. Income may not be useful in this variable. This income may not be useful in this model. We would want to rerun our model without it. But the interpretation of this model says that women tend to live longer by about 12.8 years. I don't have the student spy up, so I can't follow you. Anybody not understand the interpretation? Anybody have any questions on how we interpret that? So let's redo it with our interaction variable. Data analysis, regression. Lifespan is my Y. Income, women, drinks, and the drinks interaction is my X. You all were going to let me overwrite my other one? Now, how do we interpret this? Income has stayed the same. We haven't messed with it. And it's still not significant. Should be no surprise there. Adding a variable shouldn't flip another one from insignificant to significant. Women is still positive. So in this model, it's telling us that women on average live 11.53. Drinks is still negative and about the same coefficient, so drinks has the same. But our coefficient on drink interaction is positive, which would lead us to believe that women are affected more than men, right? But what problem would there be with that interpretation? P-value is enormous. So what would that, how would we interpret that enormous p-value?
It's not significant.
It's not, there's no significant difference in how drinking affects the lifespan of men or women. We would interpret that to tell us there's no significant difference in how drinking affects the lifespan differently between men and women. Does drinking still affect your lifespan? Sure. Negatively. But there's no significant difference that it affects women differently than men. Women are not more prone to drink-related death than men. Questions on how we interpret the signs on our dummy variables or our interaction variables? You could also, I'm going to highlight this data and copy it. I'm going to create a new tab. What if we thought that your level of education might have something to deal with this? Your level of education might have something to deal with this. People who have more education live longer. You can test for it. We can see. Maybe. Don't know till you try. How many dummy variables? Whoa! How how many education dummy variables? 3 variables. So how many categories am I testing for? 4. In this case, high school, college, and graduate. So what's the alternative? Yeah, no high school dropout. No high school, no college, no graduate. You got to fall into one of those 4 categories. People who have a graduate degree have been through college and high school. So that's a person who has a graduate degree. They, by definition, are 0 in this category and this category. This one is just a high school grad with no college and no graduate school. This one has a college degree. And this person is a high school dropout. See how none of these can be, you can't have 2 ones? Everybody is in a unique category. The categories are mutually exclusive. This is called faking it. I'll go ahead and get rid of this interaction variable so it doesn't confuse us. And here's what I'm going to run my model on. Data, data analysis, regression. I'm regressing lifespan against all of these. I do have labels. That says I1. Note that I faked all those numbers. So how would we interpret this?
Education doesn't have any effect on lifespan.
Yeah, because these are, all of these are insignificant. So we would say that both income and education have no impact on lifespan. But let's assume for a minute that they are significant. Let's assume that they work. How would we interpret our coefficients? Man, if you're going to go to school, make sure you finish college, right?
But don't go to grad school.
But don't go to grad school because it's going to kill you.
Or just drop out of high school.
Or just drop out of high school. This is telling us that high school grads, that going to graduating high school costs you 3.3 years of your life. But if you go to college, you live 5.9 years longer. However, grad school takes 3 years off your life, which I can attest to. I think my advanced econometrics class took 3 years off my life. Taught by a Ukrainian gentleman. Very good friend of mine to this day. Imagine trying to learn all this, except with a Ukrainian accent. And he goes really fast on Excel. Really fast. I always told myself I wasn't going to do that. So if I go too fast, you got to make me stop. That's the interpretation of this. But then we would look over here, of course, and see that our p-values are well above 0.10, and we would probably dismiss those and say, these don't have a lot to do with it. 4 categories, 3 dummy variables. 1 fewer dummy variables than you have possible categories. Do not use sequential numbers. 0, 1, 2, 3. Don't do it. Bad math, bad stats. Your paper will get kicked out of peer review. You will never get your paper published. You will not get that sweet assistant professor gig at a tiny college, northern Idaho. Your life on Easy Street will be derailed. Have to actually work for a living. Instead, do your dummy variables correctly, get your papers published, and get tenure. Questions on how we do these? Nothing? I don't have the student spy up. Who's following along? All right, that's good. No questions on how we do these? All right. I'm just gonna touch on logit models. I'm just gonna barely scratch the surface. I've done examples of these, so I want to just touch on our binary choice models. So far, we've been considering models where dummy variables are our explanatory models, where we're explaining salary or lifespan or something with dummy variables. But what if we wanted to predict a dummy variable? What if we wanted to predict if something would or wouldn't happen? This is why I couldn't use the mortgage example or the other one I pulled up, because you're predicting a 1 or a 0. There are applications where we're predicting a binary, a 0 or a 1. Whether or not to buy a house, who will join a health club, who will go to grad school, who will get a home loan, who will die. Binary choice models, 0 or 1. A binary choice model. Again, this is the part of this slide in this book that I hate. It goes through how to do a linear probability model. A linear probability. This is where we plug our same numbers into our same Gretel or our same Excel, and we go through this. And in about 3 slides, it's about to tell you why the linear probability model sucks. And nobody uses it. It's bad. It simply gives you bad models. Predicted values are interpreted that the probability of something happening, y equals 1. Alternatively, the model may predict a probability greater than 1. The model may predict a probability greater than 1. If I flip a coin, what's the probability it lands on heads? 50%. Tails? They add to 1. Probabilities must always add to 1. This model can give you probabilities greater than 1. This says by no means is this a fatal flaw. Yes, it is. Don't use this model. It's bad. This model is only for people who stopped at slide number 26. Don't use this model. That is a fatal flaw. Linear probability model, bad. Don't do it. Here's the example we're going to use. Consider 30 loan applications at a bank. So 30 people go into a bank and say, hey, I'd like a home loan. 16 of them are approved. 14 people were told, your income's not so great, your credit score's kind of bad, you're kind of dodgy, and you have a tattoo of a rat climbing up your face. You don't get a home loan. We're going to base it on down payment, income to loan ratio, and we're going to try to estimate 1 if they receive the loan and 0 if they don't. So this loan might be in the last 5 or 6 years. When we look at things like income and loan ratio, if this were in, say, 2006, 30 loan applicants would go in and they would get 36 loans. I started reading Ben Bernanke's book. Ben Bernanke just came out with a new book called The Courage to Act, about his role as the chairman of the Federal Reserve Board during the Great Recession. And man, that is a good book. I'm 120 pages into it, about a 600-page book, and he's really killing it so far. Interesting, well written, moves along pretty quickly, doesn't dwell on his childhood because no one cares. We want to talk about the recession. Really well written book. I don't know if he had it ghost written or what, but really moves along well. I got to that one after I read The Martian. Have you read The Martian? That's worth it. That's worth 3 or 4 hours of your time right there. See the movie? Oh, come on. You people just doing stats all the time? I had to read the book so I can go see the movie tomorrow. Alright. Nobody likes sci-fi, fine. You know what you're doing in this task class. You know what you're missing right now by being here and not watching Monday Night Football?
Yeah, the Star Wars trailer.
The Star Wars trailer, right now! Once you people leave that door, I'm Googling the Star Wars trailer. They're showing it during Monday Night Football, and we're sitting in here. Wait, who's playing Monday Night Football?
Eagles and the Giants.
That's a crap game.
Yeah, everybody's just watching.
That's
the
just a
trailer.
crap game. The good game was last night. 30 loan applicants at a bank, 16 approved, so we're estimating whether or not you might be approved. Blah, blah, blah. Interpreting the coefficients, shortcoming of the linear probability model. It sucks. An impossible probability. We're not going to use the linear probability model ever. Don't use it. Stupid. Instead, we use what's called a logit model. L-O-G-I-T. Logit model. Here we leave ordinary least squares modeling behind. And we have to use a completely different, nonlinear regression function. We leave ordinary least squares modeling behind. And we use a nonlinear regression function that ensures the result is always in the interval between 0 and 1. So we're predicting the probability that our person we test gets their loan between 0 and 1. However, this makes it more difficult because interpreting our coefficient becomes more complicated and we can't use our OLS. When we go into Excel and we click on regression, do we get to pick out what kind of regression? We do not. Excel defaults to an OLS. Here's our logistic regression. We're taking a probability between 0 and 1 for all values of x. Unfortunately, the coefficients in this model cannot be estimated by ordinary least squares. A technique known as maximum likelihood estimation is used. Maximum likelihood estimation. So we're no longer using our old OLS regression model. Y hat equals beta 0 plus beta 1x plus beta 2. That can't be used here. That regression equation is no more. That regression equation is for OLS modeling. Here, we have to break out the coefficients beta 0 and beta 1 differently. This is a maximum likelihood estimation. So interpretation is different. We will have to build this equation in Excel or somewhere. A logit versus a linear probability. Our logit follows a much better 0 to 1 curve, and it is bound by 0 and 1, and probabilities cannot exceed that. Our logit is a non-linear model. It is a non-linear model. Totally different animal. Alright, I'm going to do examples of these on Wednesday. For now, I want you to notice this. So it does the example, and the example it's given, an educator wants to determine if a student's interest in science is linked to their GPA. She uses Minitab to estimate a logit model, etc., etc. Why does she use Minitab to estimate it? Then we have to estimate our coefficients, and I'll get into this on Wednesday as well. Oh, come on. I thought I said it in here somewhere. Excel will not do this. We've reached the limits of what Excel can and cannot do. Excel cannot estimate a logit model. Period. Full stop. Cannot be done. Excel cannot be used to estimate a logit model. You must use another software package Gretl does it perfectly well. Minitab does it perfectly well. SAS, R, SPSS, Stata. Effectively anything you can name that's not called Excel will run a Logit model. So I will demonstrate how to do them in Gretl on Wednesday.